Good afternoon, friends. I warm welcome to all of you in the series of mechanics of solids in the topic of shear stress and beams. Up till now in the series of mechanics of solids, we learned about the first, that is the support reactions on beams. We also studied about bending stresses in beams, and in the previous session we have studied about the introduction to shear stress. We have derived an equation on the shear stress. We solved certain numericals related to the basic fundamental equation of the shear stress. The objectives of this today's session is definition of the shear stress, to draw the shear stress distributions for today specifically rectangular sections, and solve certain numericals. Let us revise the things we have been already studied up till now. Now, in case of the bending stress in beams, we have considered purely bending moment effect on the beams. Now, in that case, a beam is subjected to a constant bending moment and zero shear force, and there will be only bending stress in the beam. The shear stress will be zero as shear force is zero. But in actual practice, a beam is subjected to a bending moment which varies from section to section. Also, the shear force on the beam is not zero, it changes from section to section. Due to these shear forces, the beam subjected to shear stresses. These shear stresses will be acting across transverse sections of the beam. These transverse shear stresses will produce a complementary horizontal shear stresses which will be acting on longitudinal layers of the beam. Hence, beam will also be subjected to shear stresses. Now, in the previous lecture, we have derived an shear stress equation. Tau is equal to F A y bar by I B, where F is nothing but the shear force acting at a particular section. The shear stress given by the above equation is the horizontal shear stress at the distance y1 from the neutral axis. Now, in the today's session, we are going to derive an equation for shear stress distribution along the rectangular section. We have to plot the shear stress distribution diagram for rectangular section. Now, precisely refer about one particular figure, a rectangular section which has been given to us right now. The cross sectional area is B is the width, D is the depth. Now, let F is the shear force acting at the section. Consider a level EF at a distance y from the neutral axis. Let us we consider a layer EF, this layer EF at distance y from neutral axis. Now, the shear stress at any section is given by a basic fundamental equation, that is tau is equal to F A y bar by I B, where A is the area of the section above y. If you want to refer a figure, it is nothing but the area of this hatching portion. We want to find out the area of this portion. So, if you let us see on this tabletop, then this is a given rectangular section. The depth available to us is D. This is layer EF. This is the hatching portion. The available depth is Y, this one. So, this available is d minus 2y. and this will be B. So area available to us is B into D minus 2y. So if let us refer the PPT, A is equal to B cross D minus 2y, that is the area of the section above y. Y bar is the distance of the CG of the area A from the neutral axis. Very interesting point. What the statement which has been told, that y bar is the distance from, this is the area A, this is the neutral axis, from this neutral axis to distance, this one is nothing but my y bar. So if you want to refer this tabletop figure, then this is the CG and this is the value of y bar, and this y bar is equal to y plus half of the distance D minus 2y, and the same thing we can visualize, and same thing we can visualize on this PPT, that is y plus half of D minus 2y. So if we are simplifying this bracket, then is equal to y plus D by 4 minus y by 2. Y minus y by 2 is nothing but once again plus y by 2, and if we take 1/2 is the common, then we achieve half of bracket y plus D by 2. B is nothing but the actual width of the section that is given to us, and the I is the moment of inertia of the whole section about neutral axis, and you know it is very well that I word BD cube by 12 because the rectangular section which has been given to us. Now substituting all the values in this basic equation, tau is equal to Fa y bar by Ib. F is the word over here, shear force acting at a section, given section. A, that is nothing but D by 2 minus y into B cross y bar half into y plus D by 2. Ib, we are simplifying this equation, and if we come out to be common terms, F by 2I, then comes to be F by 2I bracket d square minus 4y square. This is a generalized equation, that is tau is equal to F over 2I bracket d square by 4 minus y square. It is a generalized term which is used, or which is to be used to derive or to found out the shear stress at a section for rectangular section, and you can visualize that it is related with the y, the term which is proportionate to the y term. So this equation gives an equation of parabola. So from this above equation, it is clearly visualized that tau increases as y decreases. Very interesting point. It is minus y term is there. So my tau, that is the value of shear stress, increases as the y decreases. Also from the figure B, it is clear that the variation of shear stress across the section is parabola, which is shown over here. This figure refers this to be called shear stress distribution diagram, and this diagram can be achieved by a simple single equation, that is tau is equal to F divided by 2I bracket d square by 4 minus y square, the equation that we achieved right now over here. From this equation we can plot by putting the value y is equal to 0. We have an answer. Let us put the value y is equal to d by 4, we have an answer. Y is equal to d by 2, we have an answer. Similarly, the same thing will be replicated below the neutral axis because my section is symmetrical. So if you are referring the figure over here, my y started from the neutral axis. Y is 0. The tau is maximum. So at neutral axis, the bending stress variation is maximum, while as we proceed from neutral axis to the top extreme fiber, the value y is maximum, tau is 0 value. Please visualize confirmed over here, which is quite opposite to the bending stress variation. The maximum value of bending stress which is achieved at the top and the bottom extreme fibers. But in case of the shear stress variation, the value of shear stress is 0 at top and bottom fibers, maximum at the neutral axis, that we can visualize from this rectangular section. Now at the top edge is y is equal to d by 2, and hence if we put the value y is equal to d by 2, and if we are simplifying this, f by 2 I bracket d square by 4 minus d square by 4, this term will become 0 and the tau is 0. So the shear stress value for rectangular section at top and bottom fibers are 0. But at the neutral axis, where y is equal to 0, and if you put y is equal to 0, we achieve f by 2i into d square by 4, and we achieve f d square by 8i. F d square by 8i, the value maximum shear stress at the neutral axis, the answer is f d square by 8i. You can once again simplify this equation by value putting I is equal to bd square by bd cube by 12. So once again repeat, the variation of shear stress across rectangular section is of parabolic nature, 0 at top and bottom fibers and maximum at the neutral axis. Now f is equal to f over 2 pi bracket d square by 4, so this answer is f d square by 8i. Let us we put I is equal to bd cube by 12. This d square and this d cube term will be cancelled. We achieve f by bd and simplify, tau is equal to 1.5 times f by bd. F is the shear force acting at a section. BD is nothing but the cross sectional area of the section. So the whole term F by BD is referred as average shear stress, tau average. So tau average is nothing but shear force divided by area of section, that is F by BD. So substituting the above value, we obtain the maximum shear stress, tau max is equal to 1.5 times the tau average. 1.5 times the tau average. So if we know the cross sectional area, if we know the shear force at a particular section, it is easy for us to find out the maximum value of shear stress along a rectangular section, as well as we already know that the value of shear stress is 0 at the top and bottom fibers. So with this, let us we solve certain numericals related to this. Refer the figure. A rectangular beam 100 mm wide and 250 mm deep is subjected to a maximum shear force of 50 kN. Determine first average shear stress, second maximum shear stress, third shear stress at a distance of 25 mm above the neutral axis. Very interesting point. Very simple question is that. A rectangular beam of 100 mm wide and depth is of 250 mm, which has been given to us. Maximum shear force subjected for this section is of 50 kN, which is given to us. Intention is to find out first one, that is the average shear stress. Now average shear stress is given by an fundamental equation, tau average is equal to F by area. area is known to us B cross D, F that is of 50,000 in terms of Newton is known to us. So 50,000 divided by 100 cross 250 VHU 2 megapascal, that is the average shear stress. Now maximum shear stress is given by tau maximum is equal to 1.5 times the tau average. This 1.5 times tau average, that is 1.5 into 2 is equal to 3 megapascal. So VHU in answer maximum shear stress is given by tau maximum is equal to 3 megapascal. Third point, the shear stress at a distance y from the neutral axis, because the third question which has been asked to us is to find out shear stress at a distance of 25 mm above the neutral axis. If we refer this particular figure on this tabletop, this rectangular section, this is neutral axis. The total depth available for us is 250. This layer which has been given us indirectly in terms of 25 mm, this is given as y. Intention is to find out what will be the shear stress acting at the layer F 25 mm above the neutral axis. So the shear stress at distance y from the neutral axis is given by tau is equal to F by 2 pi bracket the square by 4 minus y square. This is generalized equation which is used for rectangular section. F is known to us, that is of 50,000, 2i which is a given parameter, d square by 4 d square, d that is of